This video, I'm going to prove an important theorem. If G, let me write G, if G is an abelian group, then for all A and B in this group and all integers n, we have that AB to the n is simply A to the n times B to the n. Guess we're going to prove this with three cases. The first case will be mathematical induction. If you like seeing proofs or facts like the one on the board now, you should seriously consider subscribing to my channel, as this is what we do on this channel. We prove mathematical facts and theorems and lemmas and corollaries. Now, let us suppose that n is a positive integer, and this part of the proof is going to be by mathematical induction. Well, when n is 1, it's pretty simple. AB to the 1 is just AB. But A is the same as A to the 1, and B is the same as B to the 1. So I have AB to the n is equal to A to the n times B to the n for n is equal to 1. So I have my base case. Now, for n is equal to k, we're going to assume that AB to the k is A to the k times B to the k. And we're allowed to use this assumption to prove the next case. When n is k plus 1, we have to show that AB to the k plus 1 is in fact A to the k plus 1 times B to the k plus 1. So let her show that. Let her start off with this. AB to the k plus 1. Well, I only know something about AB to the k. So I have AB being multiplied by itself k plus 1 times. Let's break off one of them. That's AB times AB to the k. The first AB stays like it is, and AB to the k, well, that's A to the k times B to the k. Using associative property, this is A times B times A to the k, B to the k. Using the commutative law, this is the same as A to the k times B to the k times B. Using the associative law inside the big brackets, we have A to the k times B to the k times B, which is A times A to the k times B to the k plus 1. Associative law says this is the same as A times A to the k times B to the k plus 1. What's in the first bracket is A to the k plus 1 times B to the k plus 1. And that's exactly what I wanted to show. I just concluded that this is equal to that, where n is a positive integer. Now, let us consider the case when n is 0. Well, AB to the 0, well, this is E. And I want it to equal to A to the 0 times B to the 0. Well, that's E times E. So, let us get two E's. This E is the same as E times E. And the first E, this first E is being replaced with A to the 0, which is also E. And The second e is being replaced with b to the 0, which is e. So I have ab to the nth power is equal to a to the nth power times b to the nth power when n is 0. Okay, so I covered 0 and positive integers. Now let's talk about negative integers. I'm still going to let n be a positive integer. We want to show that ab to the negative n. So that's, if n is positive, negative n will be a negative integer. This is a to the negative n times b to the negative n. That's what we want to show. Well, ab to the negative n, this is ab inverse raised to the nth power. But this is b inverse times a inverse raised to the nth power. Well, b inverse is just an element in the group. A inverse is just an element in the group. And the group is commutative. The group is abelian. That means I can switch the A inverse and the B inverse to the nth power. And still, A inverse is just an element in G, and B inverse is an element in G, and that product is being raised to the nth power, to the positive integer. We already proved that it's the first element to the nth power times the second element to the nth power. But that's the same as, just multiply. That's the same as a to the negative n times b to the negative n. I started off with this, I showed it equals that, and that's exactly what I wanted to show. And since that's the last case, this is the end of the proof. Once again, if you like watching mathematical proofs like this, subscribe to my channel. Please leave a comment, click the like button. Hopefully I'll see you folks in the next video. Never forget, watch and learn.